Alright, so this week we are going to talk about networks and flows. So these things is applicable to real life. So imagine you have the internet, for example. Uh, Everyone is connected to for example some social media. Everyone is connected to someone, to several people, and if you look at this as a two direction, it's a digraph. So you might send a message to some of your friends, I mean your WhatsApp friends, and you send a message to them or you receive a message to them. Okay, so we are interested in how to formulate the situation in graph theory language. So a network, which we call NXY, is a directed graph, but not only that. So let's say it's a weighted directed graph. So on every arc, so by a directed graph, we usually use V and A for arcs. So for every, so let me, for example, D equals VA. We for every arc, where each arc, for example, A in A, is assigned with some weight. So, well, the weight will be a function. So let's say some weight. So maybe we don't use this. So it's also called a capacity. Okay. So basically, for example, the maximum speed that you can allow you to send messages in the internet, for example. Okay. So this is kind of a definition. So more precisely, we use C to be a function from A to the non-negative real numbers. Okay. So it takes non-negative real numbers. Okay. So let me. What is x and y? So x and y just two vertices. Okay. So we have two specified vertices. We are in particular interested in how messages or flows or whatever you can imagine start from x and end at y. So you probably you have some message you send from x and through several people and eventually arrives at y. Okay. So definition. An xy flow on this network NXY. So on this network NXY, each edge there is each arc there is for example CA. It's a number, okay. But flow here it's something. Imagine something exists in this network, and it satisfies this so f, which is a function from the arc side again to the negative real numbers, such that 1 for each x, which for each vertex v which is not x and y, some intermediate vertex, the value of x on the vertex v is smaller or equal than the capacity of v. So you can imagine you have some speed limit on each arc, and your flow does not exceed that speed limit. Okay. So second, right, for each sorry, what I'm saying here. So I mean for each arc in A, f of A is at most C of A. Okay. So here I want to say something else. For each vertex, which is not x and y, we need f plus of v equals f minus of v. So this is the what we call flow. So the in degree must be equal to the out degree. So how much water or whatever flow into a vertex, it must also flow out, with the exception only at x and y points. Okay, so for example here I think I need to make it precise. I didn't define what is f plus of v. It's just the sum of all the f of the edges such that edge starts from v. Okay, so it's a natural definition. This is my vertex v, and maybe I have seen 3 edges coming out of the vertex v, and maybe this guy is c1, this guy is c2, c3. It's the 3 values, 3 weights on these 3 edges. This edge is called e1. It has weights. It has weight c1. So therefore, f plus of v is just the sum of c1 plus c2 plus c3. Just this. Okay. So and similarly, f minus of v is just the sum of all the edges that arrives at v. We put f of e. Okay, so something like this. You just put the sum, this is v, of all the in-degree vertices, edges with their weights. So the sum of their weights. Okay, so some standard definition. So we call all 0 flow. So if your flow assigns 0, it's allowed to every vertex, then to every edge, then this is called 0 flow. Okay. So it's allowed. So it's a little special. You don't flow anything. Okay. Right. So another definition. So there are several things. So another definition. If for a flow f, if an edge, an arc A, f of A equals the capacity, so it reaches its maximum allowed value, then we say this arc A is saturated. Okay, this is a name, a notion. Okay, right. This arc A is saturated. So you can imagine that we start from 0 flow, and we try to increase this weights of the values of the flow. But remember, we have to satisfy this. So for flow, the in degree must be equal to out degree for every vertex. So there are some restrictions. All right. Another definition. Exercise. Definition exercise. So in a network, n equals nxy. We define the thing. We define the value. For example, f is a flow. Okay, is xy flow. f is an xy flow. Then we define the value of f, the value of the flow, which is VAL of f. It will be the difference of f plus x minus f minus of x. Okay, so at the vertex x, let's consider how much flow is going out. Okay, so you put f plus minus f minus. This value measures the balance, kind of how much flow in total you are going out. Okay, so this is called value of the flow. And I say it's an exercise. I want to leave it as an exercise to check that this is also equal to f minus of y minus f plus of y. Remember, here x and y are very special. So this is x, I do something this, like this, and so on. And this is y. So you see? So for any other z, for example here, we know that f plus of z equals f minus of z. So this difference has to be 0. However, at vertex x, it's not necessary to be 0. If at a point at vertex x, this thing is 0, then the value of f is 0. We define value of f to be this thing, not necessarily to be 0. Okay, so it measures how much flow is getting into the system and from x, and also it equals how much flow is getting away or out of the system from the point y. These two things are equal. This requires a proof. It's not difficult, but it requires a proof. Okay, so let's finally let's state a proposition. All right. Let's say a flow is given. A flow f is given on the network nxy. Okay, so it assigns weights to every arc. So let's say x is a subset, vertex subset. It contains x, the vertex x, and not contain the vertex y. You can imagine it's a subset of the vertices which contain x, but not contain y. Okay? So something like this. Then I'm going to prove that the value of f is actually equal to f plus of x minus f minus of x, big X. So you can imagine how many things are flowing out of x and how many things are flowing into x, and make the difference. So this definition, I think it should be clear, right? F plus of x is just all the edges which starts from vertex from x to a vertex from x complement, and then you look at the value. Okay, so I don't write the definition. It's very clear. It's very similar to f plus of some vertex v. So now it's a subset instead of some vertex. So the definition is clear, right? The proof is not so difficult. It's basically tracking the definition. So by definition, remember, for each v in x, I'm taking any vertex in x. So let me try. So I want to understand what is f plus of v minus f minus of v. So if v is not x, remember, v cannot be y also, so because x does not contain y. So v is not x, then we know this is 0. Okay, so this is what a flow has to satisfy. Okay, remember? Okay, let's come back. Then if we is x, so what is f plus x minus f minus x? It is a value of f. Okay, this is again our definition exercise here. So we make the sum. Most of the vertices, the sum of this thing is 0. Only this guy is not 0. So clearly, if we make all the v in x, f plus of v minus f minus of v, this thing, the total sum is value of f. And this thing is definition. Okay, the first one is f plus of x, and the second one is f minus of x. So basically definition. Okay. So we are really getting into this into some depths. So we define f, the flow, to be maximum if the value of f is maximum. So we try to find a flow which has the maximum value. Okay, we can start from 0 flow, it has 0 value. So you try to add some value to it. So you try to put more stuff into the system. Okay? Right. So remember, what is a cut? So that let's recall another definition. Recall that a cut, an edge cut, is just an edge subset which will disconnect the graph D, and which has to disconnect the graph D, and it is minimal in the sense that if you remove one edge, it will not disconnect D. Okay, so it's kind of it's a minimum subset of edges with which disconnect D. So this edge cut. We will consider the something called a minimum cut. So, but this minimum means that the value of the cut is minimum. It's just the minimum value of, let's say, E, so all the arc in this cut f of A. Okay? So you choose, for example, how this complicated graph. You choose some cut. These 3 edges form an edge cut, for example, and you have some values on it. But this, this capacity. This I put a capacity. Okay, and C1, C2, C3, and are the capacity of the flow on these 3 edges, and you make the sum. So the idea is that you try to find the weakest edge cut. Okay, so basically you find this edge cut with several edges, and the sum of all these capacities is the minimum. Okay, now we are ready to state this theorem. Okay, theorem is a kind of right. It's kind of important. So the maximum flow it has a name. The max flow mean cut theorem. So it states the following. In the network NXY fixed, the value of a maximum flow is equal to the value, the capacity of minimum cut. Okay, there are many definitions. So capacity is the function c, while the flow we use f. Okay, we can choose the flow such that it is a maximum, but the capacity is already fixed. The flow has to satisfy that at each arc, the value of each arc A is at most C of A. Okay. So this is a central theorem in this area. All right. I think I want to do something different, because the proof is a little longer, so it's not very short. I want to start the proof and not finishing it. So let's meet and finish this proof. Of course, I will repeat. I hope this is easier for you to follow. Give you some space because it's a very long proof. So at least let me finish one direction. Okay, so let's prove this. So suppose K is a minimum cut. But imagine it's any cut. Actually, for any cut, if we can prove that any maximum flow, actually any flow, its value is smaller or equal than the capacity of this cut, it's enough. Okay, but anyway, let's take K to be a minimum cut. All right. So then, to imagine this is just a subset of edges, and you have some weights. Let's say C1, C2, C3, C4 on this K, and the sum of these four capacities gives you the capacity capacity of K. Okay, so we are trying to prove that any flow, its value has to be smaller or equal than the capacity of K. Right. So the set of edges, let's look at something called the set. The set of vertices that are reachable from X. Okay, so what does this mean? Right. We call this set X. All right. What am I saying here? So I want to prove that f plus of x, the thing, is smaller or equal than capacity of K. All right. What do I mean by reachable? Because X can, in principle, it can contain the vertex Y. Okay, I got stuck. So I think it's a nice place to stop here, and I will reorganize this. And when we meet online, we continue to talk about this theorem. Great. So we are really entering the core of structural graph theory. It's it goes beyond our course. There are a lot of things. There are a lot of beautiful theorems and conjectures, and I admit it's becoming more difficult. Uh, let me try to finish. Let's start. Let's try to finish the proof of this theorem. This theorem saying that I'll repeat. So the max flow mean cut theorem. Let's look at a flow which we call nxy, a network which we call nxy. So it's just a direct graph with the capacity function, and f is a flow, as in not flow. So we consider all the flows. So the value we consider all the flows, and we take the value of a maximum flow. Flow is equal to the capacity of a minimum cut. Okay, so we start a proof. So I got stuck from my recording. So it actually is not very difficult. So the proof, the first part of is this direction. We take a cut, which is a minimal cut. K, for example, something like this. So probably you have some, maybe you have some arcs going from this direction to this direction, but this cut, okay? So it separates the whole vertex graph into vertex of the graph into X and X complement. Okay, so sometimes this cut we also denote it as in this way. So it separates some two parts. So clearly X is here and Y is here. So for X, we are going to look at F plus of X, so which is all the arcs going from X to X complement, and we put the sum of the capacities. Okay, so this sorry, sum of uh, the values of the flow on this cut. So this thing is smaller or equal than the capacity of K. Okay, and on the other hand, the value of the flow, as we already explained, it is F plus of X minus F minus of X. And this is at most, this is some number which is negative. So this is at most F plus of X, and this is smaller or equal than capacity of K. Of course, this is one direction. And then the other direction is more difficult. We are trying to prove that this maximum flow of the network, it is greater or equal than the capacity of a minimal size. Okay, so we take, in this direction, we take a maximum flow, F. And our goal is trying to prove that the value of F is greater or equal than the capacity of a minimal cut, any cut actually. So the mean cut. No, sorry, minimal cut. It has to be greater or equal than the capacity of a minimal cut. Okay, this is what we are trying to prove. Okay, so now we define X to be all the vertices all the vertices so all the vertices such that, so let's say is a subset, so let's say x, define x such that a vertex v belong to x if and only if there is a directed path. Let's write x equals v0 to v1 and so on to vk equals k. Okay, so there is a directed path from x0 to vk to v. Okay, such that either for each I here, for each draw j, vj plus 1, this arc belongs to A. So what I'm saying that is there is two situations. There are two situations. So either this is part of my graph. You have this. So okay. So this is part of my graph. You have this, for example. Okay, and this is a part of my path. So we have to the thing is I have to compare the orientations of my path and the orientation of my graph. They might not be the same. Okay, so either if this if I look at this path, I look at vj and vj minus plus 1, it is actually an arc in my graph. Okay, and sorry, I think I need to define something. Okay, so and it is unsaturated. I think I defined this in my recording. So if because we have a network with this capacity function, if f of some arc is smaller than the capacity, so this is not equal. It's strictly smaller. Then we call that this edge is unsaturated. So maybe I didn't define it. This is my fault. Let me define it now. Okay. So let me put a definition here, which I should do it earlier, but okay. So definition. So an arc is called A in A. Is called unsaturated. Okay, if f of A is smaller, strictly smaller than C of A, the capacity of A. So if you look at this arc, you can increase only looking at this arc. You can increase the value of f at this arc because the value of f is at most C of A. It's a capacity. Okay, it's the maximum speed you're allowed to flow there. Okay, so there is some space still, so we call it unsaturated. If it is equality, then we say it's saturated. Okay, so here we are looking at a path such that either, so look at this directed path and every edge, every arc here. If this thing is unsaturated, of course it belongs to my graph and it's saturated, or so the orientation is different. With vj plus 1, vj belongs to A. That means that vj plus 1 does not belong to A. Okay, so two situations, either or. Then okay, so okay, so it's a long definition. I'm looking at all the vertex at V such that you can reach V from X with a path like this. Either every arc is belong to A, or and also unsaturated, or the opposite of the arc belong to A. Okay, so either, for example, I write black, the capacity is 6 here and 5 here, and my red is the path I'm looking at, part of my path. This is V1, V2, V3, for example, and my flow along this is 5 smaller than 6, and this is 4 smaller than 5. This is okay. Or we have the situation that okay, this is my network. I have 6 here and 5 here, and my flow is maybe this is 5, and this is another direction, and this is let's say 3. So this direction, this orientation is different with the orientation of my graph. Okay, so either it belongs, but here you can so here you ask f of vj plus 1 vj, this is positive. Okay, so you ask this to be positive, so it does not has to be smaller, to be compared with the capacity. So you have this to be, for example, 0.1, doesn't matter, it's positive, is okay. Okay, so in either case, we unify the notation. We call the path is unsaturated. It's a little abusing notation, okay? Because here actually unsaturated is only one case. So when this orientation is different, we also put it and put it together as and call it unsaturated. Okay, so X is the set to sum up, is a set of vertices that is reachable through a path, a directed path. By unsaturated arcs. Okay, so in one word to describe the situation. So it contains a lot of information, but the next claim will tell you why. Okay, and the proof, the subsequent proof will tell you why we have to make such a definition. So we claim that y is not in X. Okay, you cannot, in other words, you cannot reach from X, reach Y through such a path. Okay, so proof of the claim. Suppose otherwise. Suppose we have this. X is V0, and it goes to V1, goes to V2, and it goes to Vk equals Y, right? So have this kind of a path, and this path is not saturated. Okay, so what are we trying to do? So we take, I mean, it's not saturated, meaning that each arc has 2 possibilities. We take a small number epsilon, such that we have to take this to satisfy 2 things, such that if this vi vj vi plus 1, right, f of this is so this actually this is belongs to A. Okay, and we know that f of vi plus 1 is smaller than capacity of vi plus 1. This is the first case. In this case, we need the epsilon to be smaller than this difference. We ask this epsilon to be in this case, we ask f vi plus 1 plus this epsilon is still smaller than the capacity of vi plus 1. Okay, so in another case, if vi plus 1 vi belong to A, so this is another situation. So depending on the 2 situations, this either or 2 situations, if this happens, then we know that f of vi plus 1 vi. Okay, it is a positive number. So in this case we only ask epsilon to be smaller than this positive number, smaller than f vi plus 1 vi. Okay, so there are a lot of information. So I hope so maybe you just trying to get the big picture, does not get lost in all the details. So different people feel different details differently. So they probably I give 5 different information and you receive 3 very quickly, and you probably feel slowly in another 2 information. Then for now, forget about it. Let's focus on the main idea, and then maybe later you can review. I think this is the fastest way I can imagine to get a complicated proof. Okay. So here, let's keep reviewing what we have done. We have defined this set X using a sort of unsaturated path. And to be unsaturated, there are 2 cases to consider. Okay, one is that along this path, depending on the orientation. Okay, if the orientation of the path is compatible with the orientation of the graph. Okay, and for 2 cases, we continue to look at a small positive number, which in 2 cases satisfy 2 different conditions. And then what I do is that we can modify our f such that, for example, to another flow, to a flow which we call f prime, such that f prime has a bigger value. So this is a contradiction because we have chosen f to be a maximum flow, which has the maximum value. Okay, but here, if the claim is not true, if we have a path, unsaturated path connecting x and y, then we can modify f to obtain a bigger value, obtain a flow with bigger value. Okay, so this is the contradiction. So why I can do that? So because let's draw a picture. For example, we have v1 here, and this is the value of my graph, my flow f. And maybe we have this is v2 and this is v3. There are other arcs I don't care. So these 3 vertices are part of my path. Okay. Okay. But my graph orientation is like this. Okay. So I mean, along this path is fine. But this path, the orientations for my path and for my graph are opposite. Okay. So this is my original flow f with all this number as values. So what do we do? Remember, we start from v0, which is x, and eventually we arrive at y. So this is just part of my flow. What do we do? We found that epsilon. Then for a, we put a f prime of a equals f of a plus epsilon. We increase the value of this arc. So maybe I draw red. So here I got this is a v again, v1 again, v2 again. But the new value I put a plus epsilon. And this arc, the new value I put b minus epsilon. So I didn't write the explanation. So for b, which the orientation, whose orientations are opposite, I put f prime of v equals f of v minus epsilon. Okay, because I choose this epsilon to be smaller than this f value, so I can do that.
So this is still positive number. So what do we do if you observe the vertex V2? So recall the definition of a flow. Okay, we need f plus of v equals f minus of v for any v. So this multiplication makes the modified flow f prime still satisfies this. You can verify this. Okay. So because this, for example, this integrate increased by epsilon. But this is also integrate. So integrate that also at this edge decrease by epsilon. Okay. And if we are looking at another situation, which is along the path orientation is the same. So this is A, this is B again. It will become what? It will become A plus epsilon. This is my V prime, VK, okay, VK. So this is B plus epsilon, both plus. And in this case also, you see, the in degree increased by epsilon, and the out degree also increased by epsilon. So this identity is still satisfied. You see? So in this case, in degree increase by epsilon, and here in degree decrease by epsilon, because both arcs are in degree. But in this case, one in, one out, you get in degree increase by epsilon and out degree increase also by epsilon. So both cases, the point is this identity is satisfied. And after this, the new flow F has bigger value. Okay. So I rushed a bit, but I hope to show the picture as quick, the whole picture to you as quickly as possible. You see, this is only the claim. The claim is that you cannot reach from X to Y with the unsaturated path. Okay, so this is the claim. So the proof of the claim. After the claim, what do we do? Right, let me, it's almost done. So after the claim, we know that X contains X and X does not contain Y. So Y is not in X. All right. So we put the cut K to be this. The out cut, all the out edges, this is X. And we look at all the out edges. This edge is excluded. We only look at these out edges. And we write the out boundary of this in this notation. We look at this, and this guy K is a vertex cut. Okay, in the sense of in the directed graph. So if you delete these K, you cannot go from X to Y anymore, because you are still allowed to go from Y to X, but this is a edge cut in the sense of directed graphs. Okay, and then in this case, you see the value of F is actually equal to F plus of X. It is the capacity of a cut K, and clearly it is greater or equal than the minimal capacity. This is one capacity. Okay, so it is greater or equal than the mean, right? I'm trying to prove this direction, right? Yes. So mean value of capacities. So all the capacity of the mean cut. Okay. So, okay. Right. So this is the proof of maximum flow mean cut theorem. So there are how do you feel? Any comments? Okay, great. So what's next? Right. Yeah. Let me still do something more, but I don't think I want to finish everything here. I don't know. So let's see. So let's recall another definition. Recall that circulation. I think we proved it. We discussed this in the two lectures of algebraic graph theory. So the circulation, a circulation f on a directed graph is something that is a function f. Yeah, actually, a circulation is how to think. It's like you put a weight 1 to every edge arc, okay, and is a value 1 function. So you either choose an arc or not, okay, satisfying that for any vertex f plus the odd degree of v equals f minus of v. Okay, so a circulation means that for every vertex, now there is no special vertices x and y. So it has to be for any vertex, the number of out degree equals number of in degree. And we put 1 to every edge. Not necessarily 1. So okay, it's a real function maybe. Sorry, real function. So maybe you have f1 here, f2 here, and f3 here, and f4 here. You have to satisfy that. You have to satisfy that f1 plus f2 equals f3 plus f4. So the okay. So you allow yourself to put right. You put real numbers, and we talk about this so-called cycle space. So all such real functions. So you can think of this as real functions, okay? And this time you can even put negative values. All such real functions form a vector space, which we call the cycle space. I think using matrices, we have been able to describe this cycle space. Okay, it's related to the rank of a matrix, the incidental matrix. Okay, so right. Okay, so there is this similar, but it's different. In our today topic, when we talk about a flow from x to y, we don't ask the value of so here is x, here is y. Any questions?
No.
Okay, so right. Okay, I hear some noise. Okay, so when we talk about the flow on a network, we have two special vertices, x and y. So f plus of x minus f minus of x is not necessarily 0. Okay. But all other vertices, this is actually the value, is by definition is the value of f. Okay, and the f minus of y minus f plus of y, this is also equal to this value. So this in particular, when this value is not 0, we are not in the cycle space. It's a little different. It's a little different. But now there's a technique. So let me see. Okay, let me see if I should do this. Right, I don't know if I'm ready. I jump. Maybe I need some lemma, but let me show this Munger's theorem as the final theorem I want to prove. Okay, so it tells you the following. In a digraph, D xy. Okay, so this is just a digraph, and with two special vertices. Kind of special. We have a digraph, something like this, and you do this. I don't know what to do, and eventually, maybe you get something like this, and you do something like this, and you do something like this. I don't know. So these are just x and y are two special vertices, and then so this is just a diagram with two special vertices. Any question here? Equality? Oh, okay. I didn't see any. Let me wait. Why does the second equality starts from? Right. Did you see my recording? So it's a good question. So what happens is it's an exercise. Okay. So let me come back. Okay, good to have a question. So let me come back to this. So you have a network n of xy. So it's a direct, basically it's a direct graph. So you have x and but you have two special things. You are concerned with how things will flow from x to y, but sometimes it flows backward. Okay, so you don't know how. Okay, so for any v here, you have a flow. Flow means that you have a function assign each arc a number, and the first thing it satisfies that for any v, f of plus of v equals f minus of v. So for any v is not xy. Okay, so during the flow, during the whole process, you are not allowed to introduce more stuff from the outside world. But x is like the entry. You can allow yourself to get in some stuff. For example, waters, electricity. And y is a place you can get out some energy and whatever. So the value of the flow, by definition, is look at the place x. So maybe you have 1, 1, 1 here, and this is f plus of x minus f minus of x, right? This is 1 in this case. But if you look at the whole flow, you can prove that this actually equals how many electricity or water get out of y. So it actually equals f minus of y minus f plus of x. A simple example will be, okay, consider a path, okay, 1, 1, for example, 1, you get y. So the value of this flow, very simple example, is 1, because the value of this flow is 1, because it's the out degree of x, and it is also the in degree of y. Is it clear? Is it clear? Great. So this is the definition. So it's a little complicated when you write it down, but good question. Thank you. So okay, I want to prove this theorem in a digraph. This is something similar. Okay, in a digraph. In this digraph, for now there's no flow. There's no flow. It's just a diagram, a graph. So I draw this picture very ugly. So I have several things because I want to draw this picture as the arcs can back and forth. So let me do this. Okay, and maybe something like this. I want to put it clear. Okay, so maybe I don't know, something like this. It's a example. Okay, so this is a diagram, but I put x and y two special vertices here. So I want to prove this theorem, which is actually a small consequence of the max flow mean cut theorem. The theorem we just proved, the max flow mean cut theorem, is stronger, is much stronger. It's very nice. Here, even this Munger theorem is already very deep. So in the diagram D xy, the maximum number of arc disjoint path, directed path, equals the mean number of mean size, let's say mean size of xy cut. Okay, so what I'm saying is that the first quantity is what? So how many paths you can find with no does not use one arc twice. So in this case, you because it's I think you can find two. I don't know, but for example, this one, right? And another one, no, not two. So if I change the orientation this way, I got two, because another one is something like this. I didn't use the same arc, so I got two, right? So this, for this example, this is two, and it equals the mean size of xy cut. What is a xy cut? It's just I choose this edge E1, this arc A1 and A2, this arc A2. I look at A1 and A2. If I delete A1 and A2, I cannot find any path, directed path from X to Y. And this also, this has a cardinality too. So it's also 2. So this is something I call the mean size of XY cut. So the way, how many, so the first problem is that you try to find, look for the maximum ways passes who does not use the same arc to start from X to arrive at Y. The number is 2. And the second case is try to block. You do the opposite thing. You try to block any people to walk from X to Y. And you have to cut down or delete some arcs. The minimum number of arcs you have to delete is also 2. They are the same. So I think you can do it directly, but here we can prove this as a consequence of our max flow mean cut theorem. So remember, the difference is that here we only count, and the more general max flow mean cut theorem, we assign weights. It can be any real number. It's more complicated, right? It's more general. So how to do this? So actually, you just you assign weight, or you assign 1 to every arc. Okay. So for example, here you got 1 1 1 1 1 1 1 1 1 1. Because this is a okay. Does this make sense? Right. Okay. So this is not the flow. So this is the okay. This is the capacity function. So C of any arc A equals 1 for every arc. For every arc C in A. Okay. So we don't for example we don't need to satisfy that flow rule. It's just the capacity function. Okay. And then right. So then I take a maximum flow F. Okay. So actually, this flow has to saturate some okay maximum flow, and consider the value of this flow F to be K. Okay. So this flow has to assign some number to each edges, and it satisfies this F plus V equals F minus V for all V not equal to XY. Okay. And since the value of F is K, it means that F plus of X minus F minus of X equals K equals F minus of Y minus F plus of Y. So we modify the graph D, by adding a new edge, a new arc, which is Y to X. Okay? So suppose we have a complicated graph here from X to Y. And I add another edge, which is this edge. And this edge I put and assign value K to this new arc. So here I put value K to this new arc. And this graph, I add a new arc and put value K along this arc. And this graph, this digraph, which I call D prime, with this F prime. You see, F becomes F prime. It satisfies that for every vertex, not vertex except X and Y, satisfies that for every vertex. For every vertex, F prime plus of V equals F prime minus of V. Okay, it means, in other words, this F prime is a circulation. Okay, so indeed, I need to cite one theorem that I proved and I didn't. So a circulation is always, because it belongs to the cycle space. It's always, so there's a result I didn't prove. It's always a positive linear combination of cycles. Okay, so here the proof is a little sketch. So what happens is this. So for example, this circulation has a edge which has a value K. So it means that you have to use K cycles. You have to use K cycles to partition this circulation. Each cycle exactly use this arc once. Okay. So there exists K cycles such that the sum of them gives F prime. To translate, So for example, I find one cycle from X to Y, and this edge I use once. So this is one cycle. And then I got 1, 1, 1, 1 here, and this is 1. This is one cycle. But another cycle, but this cycle I cannot use this arcs anymore. Another cycle maybe something like this, and I use this one again. So combined together, they got this picture. So you see, this is a 2 here, and this is a 1, 1, 1, and 1, 1. This is X and Y. Okay. Okay. So eventually, if I cover this circulation using K cycles, eventually I got K here, because this is one edge. This is one arc. One X. This is one arc. I got K edges, and the remaining part is K disjoint paths. Okay. Right. Okay. So it's a little rush. I think I'm going to sorry, I didn't read your question. You said, are those the weights? Which one? Which one are the weights? Okay. So because here there is a translation. So in our theorem of maximum flow mean cut theorem, this theorem, we talk about weights, right? But here the original question is only counting. But when we count 1, we put it's equivalent to that we put weight 1 to it. But however, we have an extra edge, which we call this arc yx. But for this arc, we allow it to be assigned an integer number k. This which is the weight of this. So we translate kind of this problem to the more general problem with capacities and the weights. Okay, that's great. I'm glad you got it. I got a little rush and at the end of the proof. But anyway, there is a theorem. There is a lemma. I didn't talk, but I included it in my notes. So it's a circular. The lemma I actually cited in my final proof. So the lemma says that any circulation with positive weights can always be represented using positive coefficients and on cycles. So this is something you can read later. Okay. Okay. So the time so that's all my plan for today. So let's maybe any questions? Okay, great. Let me stop the recording.